today's agenda is mainly how to interface micro-ROS and ROS, how to communicate between them and make an end-to-end project wherein we'll be controlling using this. Hope you guys can see. This is an IMU MPU6050, and this is an ESP32, which we will be using in our session. And using this, we will be controlling a robot in Gazebo, a differential drive robot. So without any further ado, let's begin the session. So I have created the repository for this session. Before beginning the session, I would like to share this repository in the chat so that people who want to do simultaneously can do. So first, what we will do, I have created a very quick PPT. So this PPT is not created by me. I just asked ChatGPT to quickly create a PPT so that you guys have some visual to see. So pardon me if the PPT looks very clumsy, but this is today's session, and we have discussed the agenda for today's session. And so let's begin with the session. So how many, I would like to know from you guys, like how many of you guys have worked on ESP32 or Arduino before? How many of you guys are familiar? Just raise your hand. Okay. Many of you guys have worked, it seems, on this. So ESP32 is nothing but a microcontroller, just like Arduino. The reason why we are not using Arduino and ESP32 because micro-ROS requires a certain clock speed to run at, and using Arduino, that is very difficult to achieve. So instead of that, Arduino has 16 megahertz clock speed and ESP32 has a 240 megahertz clock speed. So to achieve that communication, we need to use ESP32. That's why I have chosen ESP32. So let me show you how ESP32 looks. This is the wiring diagram, but in general, this is the board which I am referring to. This is a 38-pin ESP32. It's a microcontroller. It has Bluetooth and Wi-Fi enabled in it. And this is the MPU6050 sensor, which we will be looking at today. So it is an inertial measurement unit. It is used to measure angular velocity, linear acceleration, and all those things. So it has only 6 degrees of freedom because it cannot measure the magnetometer. It doesn't have that, the magnetometer thing. So we will be using this. Yeah. So we have seen what is ESP32. We will look at it in detail as we move ahead. We know what is MPU6050. It is a 6 degree of freedom IMU. It has 3-axis accelerometer and 3-axis gyroscope used to measure angular velocity and used to measure acceleration about all the 3 axes. Okay, we know this. Now let's move forward. Let's begin. So let me open Arduino first. Arduino IDE. Okay, so this is the Arduino IDE. Most of you guys would be familiar with this. And first, I'm going step by step for people who are beginner in it. So first, I'll be burning this code in the ESP32. Let me increase the font size. So this code is regarding the I2C scanner. So here we will be using I2C communication. So let's see first what is I2C. So here in this image, you can see that this is MPU. The VCC has been connected to 3.3 volt. The ground has been connected to ground pin. And there are these 2 pins, SCL and SDA. So SCL stands for serial clock and SDA stands for serial data, the line through which the data is transmitted. And on ESP32, GPIO22, GPIO stands for general purpose input and output. GPIO22 is SCL pin for I2C communication and 21 is SDA pin for I2C communication. Before moving forward, I would like to discuss what are the few common communication protocols which we use. So in today's session, we will be looking at I2C communication protocol. So I2C communication was initially or originally developed by Philips Semiconductors back in 1980, I guess. So I2C stands for Inter Integrated Circuit. This is the full form of I2C, Inter-Integrated Circuit. It has two channels or two buses for communication. One is the SCL, which is the clock line, and other is SDA, which is serial data, which is the data line. So clock is used for synchronization, like this clock pulses are there at every regular intervals. It is used for synchronization between the sensor and the microcontroller. And serial data is the line which is used to transmit data between the sensor, which is MPU6050 IMU in our case, and the microcontroller is ESP32. So this line would be used to transmit data from the sensor. There is something known as master and slave concept. So there is a master. In our case, the master is ESP32, and there is a slave. In our case, this is the sensor MPU6050. This is the slave. So using I2C lines, you can connect multiple master and multiple slaves together, but not multiple masters, but rather multiple slaves. For examples, I have three sensors. One is this sensor, one is this sensor, one is this sensor. And all these sensors are running on I2C communication protocol. So I can connect all the three to the same bus, SCL and SDA. The difference is how does it know that at this time I'm communicating to sensor 1, then at this time I'm communicating to sensor 2. Each sensor has its own address. In our case, this sensor has an address of 0x68 or sometimes 0x69. How will we get to know this address? We will get to know this address by running this script. This is the I2C scanner script, which will tell you how many I2C devices are connected to the master device, which is ESP32, and what are their individual addresses. So based on that, you can communicate with multiple devices with different addresses. There is something known as full duplex and half duplex communication. I2C comes under half duplex communication. Half duplex is, since that we only have one line for communication. Since we only have this line for communication, yeah. So by default, there is certain address, which if you don't know how to give, you can use that address using I2C scanner. You can also give your own address. At the same time, you can also define the custom I2C lines which you want to use. By default, the ESP allows a by default, the ESP has 21 and 22 as the I2C lines, but you can define your custom I2C lines as well in the wire.begin the command. So this was about I2C. It's a half duplex protocol wherein at a time you can only send data and at a time you can only receive data. So you cannot do this simultaneously. At a time data can only be sent, or other time data can be received. Cannot be done simultaneously. That's why it's a half duplex protocol. Next, let's see, this we will not be using in today's session, but there is a protocol named as SPI protocol. So it stands for Serial Peripheral Interface. This is another protocol. So again, I2C protocol is a slower protocol as compared to SPI, and I2C was mainly developed for short distance communication between sensors and integrated circuits. SPI is also that, but SPI is a full duplex protocol. Wherein data can be sent and received simultaneously. It also supports multi-slave configuration, wherein we have one master, which is the ESP32, and we can have multiple slaves or multiple sensors or even microcontrollers. and it has 4 lines for communication. So using SPI and having multiple slaves, that becomes very hectic, the connections, because each will have 4 lines. So these 4 lines are serial clock, MISO, MOSI, and chip select. So what is serial clock? Serial clock is nothing but the clock line for synchronization. MISO stands for master in, slave out. That is, this is the direction wherein the sensor will send the data and the master will take input and the slave will send output through this line, through the MISO line. And then there is MOSI, which is master out, slave in. This is this line, wherein master, the ESP32 will send data and the sensor will receive the data. And this is the chip select line. Like in I2C, we had specific addresses. In this case, we don't have specific addresses. We connect these 3 lines common, but the chip select line is different. So in one sensor, the chip select line will be connected to, say, GPIO 2. But for other sensor, the chip select line will be connected to GPIO 5. And the moment the chip select line is high, that in that case, the SPI knows that I have to send data to this sensor and not to the other sensor in which the chip select line is selected. So I2 SPI differentiates by using the chip select, not the individual address. And it is a full duplex communication. This was about SPI protocol. And then the final protocol, which we will discuss, the 3 major ones. There are others as well, but these are the generally used. Serial protocol, or you also call it UART, Universal Asynchronous Receiver Transmitter. So it has 2 lines, TX and RX. This is the most basic kind of protocol. One line is used to send data. For example, this is the microcontroller and the microcontroller transmits data. This is the sensor, and the sensor sends the data and the microcontroller receives it. So again, this is a communication protocol, 2-line communication protocol. It is a full duplex protocol wherein you can send and receive data asynchronously. There is no clock in it. It is asynchronous. That's why it is not synchronous or synchronized. So no clock is present. But these two have clock. So these are synchronous protocols. So in today's session, we will be using this protocol, the I2C protocol, for connecting our MPU6050 to our ESP32. So for that, I showed you this is the connection diagram. However, you can use the same MPU6050 and not connect it using I2C, but rather connect it using SPI. That also can be done. There is one more pin in this. I guess in this diagram, the pin is missing. There is an NCS pin. So in that case, you will be using SCL, SDA, ADO, NCS. For that, you can connect it using SPI as well. But for simplicity, today we'll be using I2C. But if you connect the same sensor using SPI, you will get a higher sample rate. But for today's requirement, we don't need that sample rate. So this is done. So if any of you guys have doubt till here, you can ask, unmute and ask. Okay, then let's upload the code and see. So this is our I2C code, I2C scanner. I will connect my ESP32 with my PC. So this is my ESP32. I have connected it with my PC. These are some random values which are coming because of the earlier code which is uploaded in it. So what I will do is I will go to the tools. I'll see if the correct port is selected or not. Where I can see that the correct port is selected, I will just upload this code. If you're asking that, you have to connect VCC to 3.3 volt and make sure that VCC is not connected. Yes, for VCC, provide 3.3 volt. In my case also, initially I was giving VCC 5 volts. So it was not recognizing the sensor. In my case, the sensor which I am using. So then I connected VCC to 3.3 volts. So then it started recognizing it. There is one issue at my end. I'm using a USB converter because I have few slots here. So I guess that might be the problem. But anyways, I know the address for this is 0x68. So I will be uploading another code for it, which will be this code, wherein we will be using the MPU6050 and reading the data on it received from it using telemetry viewer. So this is the code here. And before that, let's see how to, okay, first let's see how to view the data, then we will see how to set up telemetry on our system. So telemetry, we used to visualize the data using graphs. Okay, so here in this code, I'm using this library MPU6050TOCKN, because this library allows us to get the data from MPU using just this command. So for simplicity purpose, I'm using this library, but I would not recommend if you want to do some deep work using MPU, because it doesn't offer that much functionality. So here in this code, I'm using this library. Buyer.h is for I2C communication. And this is the sync byte which we are defining. Again, this is used for telemetry viewer. And here we are creating the MPU object, and we will be capturing gyro data, which is velocity, angular velocity in radians per second. And we will be capturing the angular data, which is in radians about X, Y, and Z axis. Here we are using the baud rate of 115200. So baud rate is nothing but the bits per second, the communication speed at which we want the serial communication to run. And here we are doing wire.begin to begin the I2C communication. We are doing MPU.begin. And here we are calibrating our MPU. And here this function, we are simply, so this is the void loop. This is the loop which continuously keeps on running in the Arduino IDE. And here we are just updating our MPU to get the recent values which it is capturing. So before viewing it on the telemetry viewer, let's first try to see if the data is coming on the serial or not. Okay. So I'll upload the code. Hopefully the data should come, or else I'll have to move the. Okay, so uploading is done. Let's see if the data is coming or not. Okay, so most probably the issue is with my USB connection. Let me just change it. Okay, so yeah, that was the main issue, because I was using a USB extender. Sometimes that won't work. So here you can see that the data is coming. And now if you run the I2C scanner, even the address of the MPU6050 will come. Initially, it was not coming because of the USB error. So here you can see the data, but this data is not intuitive at all. We don't understand anything using this data. So to make it intuitive, let's run the same data on the telemetry viewer. So before running that data on the telemetry viewer, we will have to upload the telemetry viewer code in here. So to send data on the telemetry, you have to follow a specific format which the telemetry viewer itself provides. So here we are capturing the data, the gyro data, XYZ, and here we are capturing the angular data, the angles in radians, XYZ. And here we are publishing the data in this format, wherein you have to send a sync byte first, which is 0x AA, and then you'll have to send the data in this specific format only for the telemetry to read. This is not something which I have done. This is what the telemetry provides us as a structure to use. Okay, so I will quickly upload this code to the microcontroller. So the code has been uploaded to our microcontroller. Now let's go to telemetry viewer. Once I'll show you telemetry viewer, then I'll show you how to set it up at your end. So this is the telemetry viewer. I am importing a config file which I have created like before only. I'll be sharing with you guys as well. So here you can see that the data from the MPU is coming. Right now, only 3-channel data is coming. If you can see that when I am moving the MPU, the data is changing. And at the bottom left, you guys can see that red represents GX. So Gx is the angular velocity in radians per second about the x-axis. So you can see that there are 3 channels of data coming right now. X, the red one is the this angular velocity about x-axis. Green one is the angular velocity about y-axis, and the blue one is the angular velocity about z-axis. Now let me enable the angles as well. So right now only 3-channel data is coming. Now 6-channel data will start coming. So here you can see that the angular data is also coming. Let me disable the angular velocity and then it would be more intuitive. So right now, if I rotate the sensor about z-axis, which is like this, you can see the angle about z changed. Again, the angle about z came to where it was. If I rotate the sensor about which axis? Blue is the y-axis. Okay. So this, I guess, this direction is the x-axis. The angle about x-axis changed. And if I rotate it like this, then you can see that the blue one, y-axis, changed. So here you can see intuitively that you'll get a hang of it, like how IMU works and how individual accesses data are changing. So this was about telemetry viewer and how to set it up. So it has something known as sample rate when we will be working on advanced projects which require very high sampling rate. Then instead of using I2C protocol, we will be using SPI protocol. Okay. So this was about telemetry viewer. I'll disconnect it and now I'll quickly show you guys how to install this at your end. So to install telemetry viewer, you can go in this repository provided. In the README, you will see here, download from this link. Just click here. Here you download the first version, telemetry viewer v0.8.jar file. Okay, so it is a Java JDK kind of file. You download that. Once you download and the download is complete, and again you come back here, wherever your file is downloaded, just go there and run this command. First, you have to make it an executable that you do by chmod +x and then the file name. Once it is made an executable, then you just run this command and your telemetry viewer will get opened and it will start running. Then you have to create a config file. So you don't have to create that. I have already provided the config file. You can find it in this IMU visualizer firmware. Here you can see the telemetry config file. You just put that file, copy this raw code, this one which I just flashed in the ESP32, and it will start running. Okay. So now we are successfully able to connect our sensor. We know the address of our sensor. If you don't know, you can find using I2C scanner. And we have viewed the data coming from our IMU in the telemetry viewer as well. Now we want this same data and we will publish the same data to ROS2, and there we will try to move a cylinder in RViz using the MPU6050. Then we will use it to drive a differential drive robot. If till here any of you guys have any doubt, you can just unmute and ask. Okay, so now this is done. Now let's go to the MicroROS code and use that. So we will be using this same library for the MicroROS data capturing. And besides that, okay, so before setting up MicroROS, again, how to install MicroROS on your system, what you do is just go to the README here. And here you click on MicroROS Arduino, this link. Will you please give overview from starting? Overview, we just discussed what are communication protocols, what is MPU, what is ESP32, telemetry viewer, how to get data, I2C scanner, and all those things. Okay, so MicroROS, you went there. Now you just do download zip. Once your zip is downloaded, you extract it and paste it in your libraries folder, wherever your Arduino libraries folder is present. Or there is another way, you can go in the package manager here and type MicroROS, but I did not do it like this. I don't know it will work or not, because for this, I guess you have to paste some preferences before. So I would suggest to do that way, wherein you just download the zip file and paste it in your libraries. How will you find the folder where your library is located? So here you can see include library, you can see add zip file. Either you can directly add the zip file as well, or here you can see manage libraries, or you can. So what I'm referring to is this. For Linux, Arduino is in the home folder. You go here in the Arduino folder, whatever zip file you have downloaded, either include it through the add zip one or extract it, go in the libraries and paste the extracted version here, just like this, MicroROS Arduino. It will start working. MicroROS in Windows, I'm not sure because I haven't worked. So with Windows, I'm not sure if you can install or not. But MicroROS is about microcontrollers. So I think that you will be able to install on Windows as well, because it's not about Windows, rather it's about the microcontroller which you are using. On Windows, you have to interact it with ROS just the same way you are. Yes, WSL will work just the same way you are doing with Ubuntu or Linux. Okay, so that is how you will set up MicroROS in your system. Just download it, zip file. I hope you guys know how to download the zip file. So now we have set up MicroROS on our system. Now we will go to. So once you set up MicroROS on our system, on your system, you can go to examples, and here you will see this MicroROS Arduino, and it has plenty of examples here. But most of the time, at least in my case, the examples won't work directly. You have to make some minor and major changes for them to work, such as domain ID and all those things. So few parameters I will cover in this program, and I'll share it with you guys so that you can directly copy and run it. Okay, so this is our MicroROS IMU program. So this is the basic structure which you have to use in MicroROS. So this program, what it does is, okay, so first let me explain what is MicroROS and how is it different from ROS2. So ROS2, again, you guys know that it is a framework, stands for Robot Operating System, but it requires a full operating system like Windows or Linux to run on. It cannot run directly on these tiny microcontrollers. ROS2 cannot directly run on microcontrollers. But if we want to run ROS2 on microcontrollers, there is something known as MicroROS. So MicroROS is the toned down version of ROS2, which we can run on microcontrollers. And the benefit of it is, let me show it visually. And so the benefit of using the major benefit, which I find is very useful for using MicroROS, is that if you guys have built a hardware, if you guys have worked on a hardware robot, so for example, I have this robot, which is a physical robot, and I have a Raspberry Pi installed on it. So Raspberry Pi is nothing but, you can call it a personal computer, kind of. So it can run a full-fledged operating system. Since it can run a full-fledged operating system, it can run a ROS2 on it. So this is RPi, which is running ROS2 on it, but I have motors here. For example, this is my differential. For example, let's say I have a motor here. Now to control a motor, either Raspberry Pi offers GPIO pins. Either you can use GPIO pins to control your motor directly with a motor driver in between, of course, or else motor won't run. So with a motor driver in between, either you can use this, or you can use or you have a Raspberry Pi and you have a microcontroller in between, say ESP32, and you have a motor here and you have a motor driver here. Now, why do we need motor drivers? Again, because motor run at high voltages and high current. This tiny board cannot provide that amount of voltage and current. So motor driver is used as signal amplification devices, wherein I just send it the signal and it provides the 12 volt, which has not signal amplification per se, but you can call it. It provides 12 volt to this motor. Based on the signal it is receiving, it is running the motor accordingly, based on the PWM or the DIR signals, direction signals it is receiving. So in short, if you are using Raspberry Pi GPIO pins, then you are running ROS2 directly on it, and at the same time you can run motors using it. So the nodes, the ROS2 nodes, can directly interact with the motor and run it on Raspberry Pi if I use the GPIO pins on Raspberry Pi. So if you guys have worked, which I think many of you would have worked, so there is something known as hardware interface. ROS2 control, you have to write a hardware interface so that your robot, the ROS2, can interact with the microcontroller. So the hardware interface is written in C++, and it is quite a steep learning curve, and it is difficult to write as well. Once the hardware interface is written, only then the ROS2 running on your Raspberry Pi can communicate with the microcontroller, or else ROS2 cannot directly communicate with the microcontroller. If you mean what I am saying, in the sense what I am saying, it can communicate, but not directly via topics. For that, you require a hardware interface. But what MicroROS offers us is that, uh, for example, in my case, I have a laptop here. This laptop, without any hardware interface, can directly communicate with ESP32 directly via topics. This is the the best advantage we have using MicroROS. So in my laptop, for example, let me show you one thing. In my laptop, I don't have any GPIO pins. I don't have these pins. These pins you can see here, to which the sensors are connected. I don't have any GPIO pins in my laptop. Now, how do I connect the sensor to my laptop? I cannot connect my sensor to the laptop directly. So I'm using a microcontroller. So since I'm using a microcontroller, I cannot directly communicate with my microcontroller using topics. For that, if I want to communicate and I don't want to use topics, I'll have to write a different node in Python or C++ in ROS2 so that it communicates with my ESP32 over serial. Over the serial, the sensor MPU6050 sends data, raw data, and here my Python node catches it, then converts the data, then publishes it to ROS2, then I can read from topics. So this is a very big pipeline. But using MicroROS, I can run ROS2 directly on ESP32, rather MicroROS, and it will directly capture the data, convert the data in the topics, the message type which ROS2 understands, and directly send the message over the topic, and ROS2 can directly interact with it. I think that it will be difficult for beginners to understand, because you need to have a bit of backend knowledge so that you understand the significance of MicroROS. You need to understand the difficulty faced while writing hardware interface. Only then you will understand the benefit of MicroROS. So this is MicroROS. If you guys have any doubt, you can unmute and ask. I'll try to clear it.
Hello. Hello, can
Yes.
you hear me?
Yeah, I can hear you.
Yeah. So, does the microROS be installed on the ESP, or like we have to use a Pi for it?
No, that's the benefit. MicroROS is built for microcontrollers. So either you can install it on ESP32, run MicroROS rather on ESP32 or TIN-C, or Not sure if Arduino supports it, but I think it does not. So mm, these microcontrollers, you can run MicroROS and directly interact with ROS2. You'll see once I demonstrate how easy it is to interact with ROS2 using MicroROS. And yes, MicroROS can communicate wirelessly as well. Right now, we will be using serial, but it can communicate wirelessly over TCP UDP protocols. Even telemetry can communicate wirelessly without serial over TCP and UDP protocols. Okay. So this is the benefit of using MicroROS. So intuitively saying MicroROS is nothing but your ESP32. ESP32 will start acting as a part of the laptop itself. It will act as a ROS2 node. If you guys, for the guys who know what are ROS2 nodes, so there are multiple nodes running. For example, there is a turtle sim node running on my laptop and I can communicate directly via it. Similarly, when I use MicroROS, this ESP32 will start acting as a node inside ROS2 and I can communicate directly via topics. That's really cool. If you know the hassle which is involved in interacting using hardware interface or serial communication for that matter. ESP32 is a node in ROS2. Yes, it will act like that, that the code I am running and on it. So it will act as if it is a node and you can directly interact it with using ROS2. So let's see how that is done. And on the way, if you guys have any doubt, I clear it. Will Arduino Nano ESP32 act as ROS2 node as well, just like a regular ESP32? I guess if it has Arduino Nano has ESP32 on it, the version which you are talking about, it should. Okay. So this is the code. So we have installed the MicroROS library. This is the package or the library which we are using, the MicroROS. And these are the other things which needs to be included while writing this code. This is the general structure of it. So we will be using this message type. So there are nodes, and as you guys will be knowing who are familiar with ROS2, there are nodes, and the nodes interact with each other through topics, and the way they interact are through messages or message types. Okay, so the messages have their own types. So let me just show it quickly for people who are new. Okay. So here I have a node, say N1. Here I have a node, say N2. This is a publisher node. Now, what is a publisher node? Publisher node is a node that performs the action of publishing something, publishing a message or sending a message. And subscriber node, subscriber node is again a node which performs the action of subscribing or receiving data. How do these two communicate? These two communicate via something known as ROS2 topic. This is the topic. You can name the topic anything. For example, let's name this topic as CMD well, command velocity. This is the general topic in ROS2 through which all the velocity commands are sent to the robot. This node sends the sensor message to this topic. This node subscribes it. The only thing which you have to keep in mind is the type. Message type, if it is sending integer data, this node is sending integer data, this node should also subscribe integer data. That is, this topic only accepts integer data. You cannot send string type data to this topic, or you cannot send char to this topic. Okay, so the only thing you have to keep in mind is the message type. Message type should be consistent. So when we are using IMU, we use this message type from sensor messages package. In the messages folder, we use the IMU message type. Now, what is there inside IMU? It has a basic structure inside it, which we will see, but we are using this message type. This is a ROS2 message type, but we are using this message type directly in our microcontroller. So that is the benefit of using MicroROS. We can directly interact it with ROS2. So if you see here, we are using this message type. Now, what is inside this message type? How will we know that what is inside this message type? So let's go to ROS2. Here I have opened my terminal. I will do ROS2 interface show, and I want to see what's inside the sensor messages message IMU. So I will do sense ROS2 interface show sensor messages. Inside message folder, I want to see IMU. So there are all these things present here, out of which I want to see this one, the IMU one. So I will type I capital, then M small, and then U, IMU. If I press enter, you will see inside this message type, sensor messages message IMU, which is used to send inertial measurement unit data. It has these things present. It has a header, it has a timestamp, it has frame ID. Frame ID is nothing but the link, for example, IMU link or base link, whatever the frame for which the data you are sending. So this is the frame ID. We will give this frame ID as IMU link further in the code. This is the data. We saw that the angular data was coming in form of Euler angles, that is roll, pitch, yaw, around angular movement along around XYZ. But using this message type, we have to send the data using in the quaternion format. So for our understanding, it's very intuitive to understand Euler angles, that is roll, pitch, and yaw, rotation about XYZ axis. But for computer, it has to do many calculations at the back end. And when the data is in the form of quaternions, it is very easy for the computer to do calculation, but it is very difficult for a human to understand intuitively as to what are quaternions and how they are functioning. So this is the general format in which we send data. You can read more about quaternions after this workshop. So we are converting this data and sending it in quaternions. We have this angular velocity wherein we will be sending XYZ angular velocity, and we have linear acceleration in meters per second. So this message type contains these things, and we have to send these things to our ROS2 topic. So inside that, that was present. Okay. So here we are using the MPU6050 wire for I2C communication. We are defining a publisher. Again, what is a publisher? I just mentioned. So in our case, this ESP32 will capture data from this sensor. The data will come via I2C, and this ESP32 will act as a publisher, which will publish data to a topic. So it will act as a publisher node, a node that publishes data. We are defining the message type as this. Then these things are again the structure. This is used for memory management and all these things. Here we are defining the node. Again, this is important. Init options. Why is it important? I'll show you. This is the same as we did previously. The points to take note of is when communicating with ROS2, make sure the ROS2 domain ID which you are using and the domain ID you mentioned here are the same. I think by default the domain ID is 0 if you have not explicitly set it. I have set it to 1, so I am using the domain ID as 1. Okay. And this is the microseconds, after how many seconds we want to publish. So basically it is 50 hertz. We want to publish the sensor data at a rate of 50 hertz. And here, this is the error loop. For example, if there is difficulty in communication or the communication is not being established between ROS2 and micro-ROS, then the LED, onboard LED on ESP32 will start blinking after every 100 milliseconds. Okay. So again, we are using a baud rate of 2 Mbps, 2 megabytes per second. And this is the thing which we have looked at earlier. This is again a main section wherein initially, if you look at the example code, I guess, I don't remember, they only have this init options. So most of the times it won't work, and it is very difficult to figure it out. So you have to add these three lines as well, wherein you specify the domain ID, which should match with the ROS domain ID, and you have to write this line of code as well. And here you name the node. So the ESP32 node will be, when we do when in ROS2, when here we will do ROS2 node list, when we will do this, this name will appear, MicroROS MPU6050 node. So this is the name which you are giving to your ESP32 node. Here you are creating the publisher, and the publisher is supposed to publish to this topic. Again, this topic you can name it anything. I have named it this IMU data raw because it is publishing raw IMU data. This node, MicroROS node, which is this entire node, will be publishing to this topic, and the message type will be this sensor messages message IMU. What is there inside IMU message? We just saw. Frame ID I had mentioned, there is a frame ID section inside the IMU. So here we are naming the frame ID as IMU link. Okay. And this is the capacity we are setting. Covariance we are not calculating, and I'm also not sure the significance of it, but we are giving it as 1. It signifies that on board we are not calculating covariance. If you want, you can calculate on your PC or the ROS2 end. But on board ESP32, we are not calculating covariance. This was the setup loop. Most of the things are here as template only. You just have to follow it. Few things you have to change, like domain ID, etc. Then we have the main loop. Here the main logic is being written. The logic is not that much, but generally we write it here. So first, this is the publish time, and this is the message counter. So we will be publishing data at at a frequency of 50 hertz. So to match that, we had given a 20,000 milliseconds. So we want to publish data after every 20,000 millisecond. So to keep record of that, we are using this variable wherein we are giving the start time as 0, and then using this function micros. So what this function does is, the moment your microcontroller starts, it starts recording time in microseconds. What do you call it? Like a timeline, it starts recording. So now when I use this variable now, it stores the current time when this function was called in the now variable. And I use this here, I'm updating the MPU, getting the current values. And then here I use the current time minus last published time, last time when the data was published. If the difference between the current time and the last time is the delay, which is 20,000 seconds I have put, then go in the loop again and publish once again. So after every 20,000 microseconds, after every 20,000 microseconds, the data is being published. That is at a rate of 50 hertz, or else it will start publishing at the maximum speed which ESP allows, which is the clock speed is 240 megahertz. We don't want that rate. So we are doing that. These are again the timestamps which were there in the header, which we are recording. And this is the data which we are recording. We are multiplying this with this to convert the degrees per second to radians per second, because in ROS2, everything is done in radians. So that's why we are multiplying this to convert the degree to radian. And we are getting the acceleration value from the sensor. And the acceleration value from the sensor is the sensor outputs it in the form of G value. 1G, 2G, 3G. The G is nothing but 9.8 meters per second square, the gravity of Earth. So we don't want in G value, we want in meters per second square. So this value 1, 2, 3, we are multiplying it with this. So we get the linear XYZ. Then we have stored everything here, and then we are simply calling the publisher object and publishing the data, this message data. This is the message data. You can see everywhere the message data is highlighted. So finally, we are sending this message, which is IMU message type, over this topic. Which topic? IMU data raw for ROS2 to receive, and there a node will receive it and do whatever it is supposed to do. And here in the last line, I have put it so that the ESP32 onboard LED blinks after every 50 times the thing has ran. So every time it sends data, it doesn't light up, or else you won't be seeing it blinking because it will be that fast. So to see it blinking, I've put this value. So message counter is doing that. After every 50 messages, it is blinking once, just to get a feedback that things are working. So this is the micro-ROS code, basically, uh, what we will be using. Right now, we will be using it as a publisher, but there in the examples, you can experiment on your own. And in the micro-ROS examples, you can go and experiment on your own and even use the subscriber code, wherein you send the data from ROS2 and this code will receive it and show it on the serial monitor here, whatever you receive, or turn on the LED, whatever you want to do. So here, if you will see that there is no domain ID defined. And if some of you guys have changed your domain ID, it won't run. The agent will not get connected. We will see what is micro-ROS agent. It will not get connected. So for that, you can use this code. This code should work fine. Okay, so let me upload this code to my microcontroller. The code has been uploaded. Now let's move to, we cannot directly see what's happening. However, we can see. Let's before making a package, let's see if we are receiving the data or not. So I showed you guys, okay, I showed you how to set up micro-ROS on ESP32. Now you have to set up micro-ROS on your local host as well, your PC. So how do you do that? Again, if you go in the repository provided, here you go to this link, micro-ROS setup tools. Click here. This page will open. I'll zoom in a bit. This page will open. This page will give you step-by-step installation commands to set up micro-ROS on your system. So you just have to copy each command and paste it in your terminal. You copied this command, you pasted it here and pressed enter, and you have to continue. So first you have to create a micro-ROS directory. Then you have to go inside the micro-ROS directory. Then you have to clone the micro-ROS repository. Once you have cloned, you have to do update and upgrade. Then you have to install the missing dependencies. Then you have to install Python 3 pip, and then you have to do colcon build. Once you do this, your micro-ROS workspace will be ready. You just have to copy paste things. Nothing else is required. Then once your workspace is ready, you have to run this script. Just have to run this command. It will like do whatever it has to do. Once that is done, again, you source it. I hope you guys know the meaning of sourcing, people who have used ROS. So you have to source it. And once everything is sourced, you have to build the agent, the micro-ROS agent, which is responsible for communicating directly with the micro-ROS running on your microcontroller. Once that is done, then you can use this line ROS2 run micro-ROS agent to communicate. Here it is using UDP, but we will be using serial to communicate. So these are the steps to set up micro-ROS workspace on your system. So I have shown you guys how to set up micro-ROS on your system. Once you have set up micro-ROS on your system, you just have to do this again. These things are there. For serial, you have to run this command. So I will go here in my terminal. Okay. Here in my terminal, I will go to the micro-ROS workspace that I have created. I went inside this. I will source the workspace, source install setup.bash. I have sourced the workspace. Now I will copy this command and run it. So what is this command? ROS to run from micro-ROS agent package. There is Okay, first let me show you the internal structure. What is there? If I do ls, there is src. You'll have to go inside src. Again, if we do ls, there is micro-ROS setup and micro-ROS again. So if I go in micro-ROS setup and if I do ls, and if I go inside scripts, if I do ls, here you will see the build agent script. So if you run this script, the micro-ROS agent will be built. Let's see, where is the micro-ROS agent package. If I do ls and go in UROS, so here you will see the micro-ROS agent package. From this we are calling. Let's go inside this once. Okay, so this package we are referring to. This is the main package which we are calling. And inside this, the script will be present. So where will we get the script? I think we'll get in src. Let's try going inside src agent. Inside this, the script might be present. I'm not going any further. It's of no use for now. Okay. So I have sourced. I will quickly copy this again and run the micro-ROS agent. But so here we are not using UDP, but rather we are using serial. My COM port is devtty USB 0, which I showed you in Arduino. And this is the baud rate. We will not be using baud rate. We will leave it to default, which is 115200. If I press enter, you'll see it is trying to connect. So I'll have to press reset on my ESP. Okay, right now my ESP is not connected. Let me connect my ESP. Okay, so I have connected my ESP. Let me press. Okay, so yeah. So the moment I pressed reset, the connection got established. Micro-ROS code is running on our system. Session established, participant created, topic created, publisher created, data writer created. Now let's see the magic. Now if I simply do a ROS2 node list, hopefully the node should appear. And it did not appear. Now let's see what's the issue. Nothing works at once. Yeah. So now it appeared because I had not sourced my ROS2 environment. I just sourced it using SC and it appeared. So now you can see that this node, the ESP32 is behaving as a node here. We can directly send messages to ESP32. Like that's really cool. If I do ROS2 topic list, here you can see I have the IMU data raw topic which I had defined in the Arduino code. You will see here. See, here we had defined this node name. This is appearing, and here we had defined the topic name. That topic is appearing. Now let's look inside the topic and see if we are getting any data or not. So how will we do that? We will do that by using echo function. ROS2 topic echo. I want to see inside IMU data raw topic. If I press enter, you can clearly see that we are receiving the data, linear acceleration data, angular velocity data, and other data as well, but the screen is short. So now if I move my microcontroller, you can see how easily I am able to interact in ROS2 directly with my microcontroller. No hardware interface, no nodes for conversion of serial data. Directly, I just ran a micro-ROS agent and I burnt a code on my ESP32, and so simply I'm able to control and get value from my IMU on ESP32. Now that I am able to get this value, now I can use it to make anything. Now it just depends on your creativity, how you can use it to like interact with anything. Just, and that's the benefit of ROS. From a single topic, I am getting data. 1 second. I am getting data in this topic. I am getting data in the IMU topic, IMU data raw. Now and which node? The ESP32 MicroROS node is publishing to this topic. Now, once it is publishing, now I can use this data coming to this topic in any node. N1, N3, N2, N3, N4, N5, and do whatever I want in ROS2. I can make any project. Once the topic is receiving data, anyone can subscribe. Just that message type should be same, which is IMU, sensor messages IMU. So let's see what is the message type of this. Let it keep running, and in this terminal, let us see what is the message type. So ROS2 topic info, I want to see information about the IMU data raw topic. So you can see the message type is sensor messages message IMU, which we used in MicroROS. And publisher count is 1. That is ESP32 is publishing to this topic IMU data raw. Subscriber count is 1 because this terminal is subscribing from this topic. So subscription count is 1. And if you want to see it visually, you can see it using RQT graph. Here you can see that this node, which is nothing but our ESP32 node, is publishing to this topic. And this is the CLI command line, which is subscribing and showing us. So this is what is happening at the backend. So till here, if you guys have any doubt, you can unmute and ask. Must be alias created to source workspace. Yes, I have created an alias to source the workspace. SC command. Yes. Okay. You guys, the data published is proper. Can we visualize it in RViz? Yes, we will be visualizing it in RViz shortly. Yeah. So now let's visualize this data quickly on RViz. So I'm stopping it. So to visualize this data on RViz, we will have to create a workspace. So we will quickly create a workspace. So to create a workspace, how do you do that? You do that mkdir. What's the delay between ESP32 and ROS2? So it is almost real time. Again, depends on the clock speed. ESP32 offers a 240 megahertz clock speed. If you use 10C, the delay will significantly reduce. But right now we are publishing at a frequency of 50 hertz. So what is 1 by 50 hertz? 20,000 microseconds. Just do that calculation in seconds and you'll get to the delay. But it is almost real time. Okay. If you want to reduce the delay to maximum to maximize the sample rate, again, you should not prefer using I2C. You should prefer using SPI communication, and you should try going with higher grade microcontrollers like 10C 4.1. Okay. So mkdir gesture underscore workspace. I'm creating a workspace. We will be naming this workspace as gesture workspace. I will go inside the gesture workspace. Here I will create a source folder. I will go, let's see, ls source folder has been created. I will go inside the source folder. There is nothing in here. Now let me disconnect. Okay. Basically, we will be creating a Python package here named as IMU visualizer, because that matches with the repository I've shared with you guys. I have already created, I guess. So, okay, workspace is different, so it should work. So ROS2 pkg create package name will be IMU visualizer, and it will be a Python package. So build type will be amint Python. If I press enter, so you should see that IMU visualizer package has been created. Now let's go inside IMU visualizer. We will have this, since it is a Python package, it will have this structure. Okay, so in here, let's create 2-3 more folders. So let's do mkdir. Let's create a launch folder, launch launch folder. Let's create a URDF folder. Let's create a RViz folder to store the RViz config. If I do ls, these folders have been created. Now let's go a bit back and open it in VS Code. To open it in VS Code, you do code space dot. Press enter. VS Code got opened. Here is your IMU visualizer. Here is your IMU visualizer package. In this, there are these folders, which we will do. So let's first create the URDF, which we will try moving in RViz. So again, let's name this as, we will create cube. Let's name it as IMU cube dot URDF. Okay. If I press enter, this is the URDF. I'll quickly just copy the URDF from here. So where I will go, I'll go in the IMU visualizer package. I will go in the URDF folder, IMU cube.urdf. I will just go and copy it. I will paste it. I'm not going into the details of how you write the URDF because this session is not oriented towards that. However, I have covered it in another session, which I will, let me just share the link in the chat box so that you guys can refer the recordings. So in the channel, you'll find the recordings of basics and the URDF development as well. In the edge avoiding robot, we will be using the same file of the edge avoiding robot, which we built. Okay, so this URDF, we have named it as IMU robot. Link name is IMU link, which we had defined in the firmware itself. This is the size of the cylinder which we are using. We are giving it a purple color, and this is the RGB to give a purple color. So basically, this is the URDF of the cylinder, very basic. Once the URDF is created, let's try to run it. Before that, let's set up the package.xml so that things get built. Again, package.xml, I'll go here. I'll copy this. I'll just paste it here. So package.xml is nothing but the dependencies which we are using. So here we are using RCL Pi, sensor messages, IMU. These things we will be seeing further when we move ahead. But these are the things which we will be using. And again, you have to do set pi. Where did that go? Let me just copy it. Setup.py. Okay. So this is the setup.py is nothing but everything is the same, just that since you have included launch file and URDF, you are defining it here that so that the system knows that there are these files as well present inside the package. And this is the entry point which you are giving. These nodes, we haven't written it now, so it might give error. So I'm just commenting it out. Okay, we will be writing this nodes as we move ahead. So this thing is done, URDF is done, setup.py is done, launch file is done. Let's try to build the workspace then using call con build. Okay, so we have successfully built the workspace. Let's get, yeah, let's source the workspace, and here let's run this command to visualize if things are working or not. So in the readme, you will get this command. So this side I will open RViz2. Let's see the URDF which we have created is coming in RViz or not. So I have opened RViz here, and here let me just paste the command and remove RViz from here. Okay, so this command we are running the robot state publisher, because without the robot state publisher you won't be able to visualize the URDF. And to this robot state publisher we are passing the full this thing path to the URDF. So this is the full path: gesture workspace, inside gesture workspace, inside SRC, IMU visualizer, URDF. I am passing this URDF to the robot state publisher so that it visualizes it in RViz. Let's see if it works or not. Here you can see the moment I pressed enter, in RViz, a cylinder appeared. But the cylinder is white in color because of this. If you do go in global options, fixed frame is odom, but since right now there is no such frame as odom present in the robot state publisher, it only knows a frame which is IMU link. If I press enter, it will become purple because IMU link is selected. This URDF which we just created now, this is the URDF which is present in RViz. Okay, so quickly what we will do is we will try to move this cylinder using the what you call IMU values. Using moving the sensor, we will try to move this cylinder. So how will we do that? Let's see. So for that, URDF is done. Now we will have to write a Python node. And this node we will name as IMUSMOT smoother smoother.py. So what this node will do is we will, as you guys saw that when we were using telemetry viewer, even when I was holding the sensor still there was the values were jittery because of noise. So if I, or even in the case when the values were coming here in the terminal, you were seeing that the values were almost constant, but there was slight change that was happening because of noise. So if we use that value, the raw IMU values directly in our system, then the cylinder will not be still, rather it will always be jittery and it will keep on moving even when we are not moving our hand due to noise. So to remove that noise, we will be using something known as a moving average filter. So moving average filter is a very common and one of the most simplest kind of filter. And the theory behind moving average filter, I'll just quickly share it with you guys. Okay. So this is basically what is a moving average filter. For example, I have input as 2, 4, 6, 8. These, for example, these are my IMU values, the 4 readings of my IMU value, 1, 2, 3, 4. This is the raw IMU value I am referring to, IMU raw. But I will not be using this directly because this might have some noise. So what I will do, I will apply a moving average filter to it. Now, what is a moving average filter? There is something known as a window size in moving average filter. So window size is nothing but we will be averaging. For example, let's consider a window size of 3. So what we will do y1, we will do this. We will add it to 4, 6 divided by 3, since this is our window size. And we will get a value. For example, that value is not theta 1, but let's say that value is A1. Okay, whatever the value. Let's say that value is A1. uh, what is 12 by 3? That is 4, and the average of this will be 4 only. So let's take this as 4 only. So y1 we got as 4, then we will apply again the moving average filter here. We will get y2, we will take the average of this, we will put it here, which will be 6, and so on. As the values will keep on coming, we will be applying a filter, and these values which we get as output, these values will not have noise or very less noise. If we want, the noise depends on the window size. If the window size is too small, like 3, the noise, like it won't remove that much noise. But for example, if we keep a window size of 15, that is after every 15 values from the IMU raw values, you just average it out and give me one value. So that will be a very stable value. It will remove most of the noise. So this is what is basically a moving average filter, which we use to average out or remove the noise so that we get a stable value. And you can increase or decrease the stability based on the window size. So what we will do is, in the IMU smoother node, we will quickly write the moving average node. So here IMU smoother, I'll just copy it from here and paste it. So this is the filter. So this is the interpreter path which we are importing. This is the message type which we are importing. Again, this is for making the queue for it. And here we are defining, so this is the node name which we are giving. Here we are defining the window size as 10. That is, after every 10 values, average it out and give me one value. And that value should be stable. And similarly, since the microcontroller is running at such a high rate, so you won't even know that you got 10 values and you got the average. So that's the benefit. Again, we are declaring parameters here. I am not going into the details of how the code is, like what is the what are parameters and all those things, because these things are covered in ROS2 basics in detail. You can check out the videos. I'm just explaining the logic. So declare parameters, we are giving a window size of 10, and then here we are creating the buffer. For example, I want to store 10 values, then I want to average out the 10 values. So I'm creating a buffer here for window size 10. So it will basically, it will create an say array of 10, like size of 10, and it will store the 10 values, 10 raw IMU values. From where is it subscribing the IMU values? From this topic. This topic, where had we defined? In the MicroROS code, in the firmware which we uploaded to ESP32, we had defined this topic, IMU data raw. I am capturing the data directly from the MPU which I am receiving, and here I have created a publisher that I want to publish the filtered value to this topic, IMU data filtered. We will be using this topic later. But so whenever this IMU data raw receives any value from the MPU, it calls this IMU callback function. Basically, this is the basic how subscribers and publishers work. So this function is called, and here it is appending the values in the buffer which we created, acceleration X buffer, Y, Z. For every value, it is appending and creating a window size of 10, that is 10 values are getting stored. The moment 10 values are in there, which this function is counting, the DQ function, moment it has 10 values, then it is going here. Again, this is, we have looked at it before. IMU message type, you have to define everything what is there inside it, orientation and covariance and linear acceleration. We have looked at it. Here the main thing is happening, we are calculating the mean of the buffer, that is the 10 values that are stored in the buffer. We are converting, calculating the average of it, which is one value, and we are publishing it in the filtered messages message type, that is getting published to the this topic, data filtered topic. So this is where the calculation is happening, just the mean we are calculating, and then we are publishing the filtered message. Now that the noisy data has been removed and this is a more stable data, we can use this program to visualize it in RViz. But before that, we'll have to do a few more things. So that we'll have to write a launch file, which I will explain you why we need to do so. We'll quickly go in the launch file section and view imu.launch. If you copy it here, view imu.launch. If I press OK, rename vimu.launch.py since it is a Python file. Paste. Okay. So again, what is a launch file? We have covered it in the previous videos, but I'm still covering it once again. So basically, here you can see that I ran one node here, which was RViz, and I ran other node here, which was this thing, or say, for example, any node. So if I want to run 10 nodes, I'll have to open 10 terminals and run 10 different nodes like individually. So it is very hectic. So what we do is we create a launch file wherein whatever nodes we are supposed to run, we just put that nodes in the launch file and we just run the launch file. So launch file on our behalf runs all the nodes. So this is basically the significance of launch files. And if your node has certain parameters, you can directly define those parameters in the launch file itself. So in the launch file, what we are doing is I just ran this node, a robot state publisher node, and I passed the URDF to this. This is what we are doing. We are getting the location for the URDF and storing it in the URDF path using get packet share directory function. We will be running the IMU smoother node, which we wrote just now. We will be running the robot state publisher, to which to the robot description topic, we are publishing the URDF path, which we just published here, but this time we are doing it using launch file. And here we are running the RViz node, which we did. So these are the things which we have already looked at. There is one more thing, which is this. Here we are using a Madgwick filter. So basically what a Madgwick filter does is that it takes all the raw values, fuses it together, the gyro value, the acceleration value, and even the magnetometer value. But in our case, since we have MPU6050, so we don't have magnetometer value, it fuses it together and gives us a more stable output and in the form of acceleration and velocity and all those things. But the significance why we are using it here is that it gives us this frame. We can put this odom frame with the reference, like the fixed frame will be odom and the moving frame will be IMU link. So I had tried putting the odom frame directly in the URDF, but somehow it was not working. I had tried a lot. Because I had published the static TF and I even tried publishing the dynamic TF, but it was not working. So I found out that using this package, using this node, we can easily do that. So this is how it is like worked for me. So world frame, we are giving it as odom. Magnetometer we don't have, we are giving it as false. Published TF, we are giving it as true. And again, gain is the sensitivity. If you put the gain as very low, the system will be very stable, but the response time will be very high. It will not be that reactive. But if you put the gain as very high, the system will not be stable and the response time will be low. So it depends on your application. So Madgwick filter is nothing but it fuses all the data together and gives you a more stable acceleration and velocity values. So this node has these topics. It has this topic. It expects that IMU data raw. It expects that you publish data to this topic IMU data raw, but we don't want to publish directly from, like, we don't want this node to subscribe directly from IMU data raw because that is the raw data. Rather, we want it to subscribe from the filtered data, which we just filtered using the moving average filter. And this node outputs the data, filtered data, to this topic. but we don't want to output to this topic, rather we want to output to this topic. So this is something known as topic remapping, again, which is covered in the previous videos. So you can remap the topics in ROS2 in real time. So this is the Madgwick filter. You can research about it after this to get a better idea of it. So basically it will publish the OTF between ODOM and IMU link. TF is nothing but the transforms. Okay, so I'll try to explain it even further, but let's see the visualization first so that we get some motivation. Okay, so we have these things ready, and since we have put this node here, so we will have to enable this node here. I'll enable it, and I will try to, what I'll do is I'll make this executable as well. So what I will do is I will go to src IMU visualizer ls. We have this node here. I'll make it executable. How do you make it executable? chmod plus x. Now this is green, that is it. It is converted to an executable. Now I will try to build. Now I'll try to build what we wrote just now, but let's see if everything is saved. Okay, everything is saved. Let's do con build. We were successfully able to build it. Now let's do source install setup.bash. Okay, now let's reconnect the MicroROS agent because I disconnected it. So I'll connect my USB. Okay, so the MicroROS agent got connected. Okay, let's go to gesture workspace. Let's build it. Let's source install setup.bash. Hopefully it should work. ROS2 launch from IMU visualizer package. I want to launch the view imu.launch.py. Yeah, this time it is also working. So I guess sometimes if things don't work out, either restart your terminal, or sometimes even you have to restart your laptop as well. So here you can see, since we have put the window size as 15, in the code we had put it as 10, but in the launch file I had put the window size as 15. So you can see how the motion is. It's so smooth. I don't know if the screen is lagging at your end, so it might not be smooth. But if you can see, like if I move the IMU about Z axis, so the cylinder will rotate about Z axis. Blue one represents the Z axis. You can see that I'm moving my IMU about the Z axis. It is rotating about the Z axis. If I move my IMU about, okay, so which one is this axis? If I move my IMU about x-axis, this is x-axis. The red one is x-axis. So more or less it is trying to move about x-axis, but since my motion is not perfect, so it is revolving about other axes as well. And this is y-axis. So it is the green one. It is rotating about the y-axis now. And this is z-axis, and this is some random motion. So here we have successfully connected the IMU with MicroROS ESP32 and ROS2, and we are able to visualize it. Okay. So this thing is done. Till here, if you guys have any doubt, you can just unmute and ask. This was a lot of things at once. ROS2 node list. Let's see if the no node is running. ROS2 top quick list. No topic is there as such. Okay. Now, now what should we do? We should first create the micro ROS agent. My ESP is connected, and here you can see that my ESP is blinking as well. If you guys can see, I don't know if you guys can see, but it is blinking after every 100 milliseconds. So that's because it is not able to communicate. So that which we had put in the code for error loop basically. So source install setup.bash. This is done. Now let's do MicroROS agent command. ROS2 run MicroROS agent serial dev tty USB 0. Let's see if it is on USB 0 or not. Let's open Arduino once. I guess Arduino is opened, and see, it is showing that my ESP is on USB 0. And also, okay, we press enter. Okay, so it is connected. Let's source it once again. Source. Now let's do ROS2 node list. We have this node ROS2 topic list. We have the IMU data raw topic. Let's do ROS2 topic echo. IMU data raw enter. We are getting the values. Okay, things are working till here. So the pipeline is not an issue. Now let's go to, is the meeting recorded? Yes, it is being recorded. Let's go to gesture workspace. Let's source. So URC source install setup.bash. Now final note ROS2 launch from IMU visualizer. I want to launch. Hopefully it should run. Oh, finally it is running. I think that that the main issue is every time I noticed that whenever here we are creating the MicroROS agent, I was not sourcing this workspace, because now just look at the nitty-gritties what I noticed, and most probably I think it's happening because of that only. So what I was doing, let me explain. Okay, here only I opened this terminal, the MicroROS terminal, and before running MicroROS I had opened this terminal as well. Like, I had divided the screen beforehand only. So whenever you open a new terminal at the backend, ROS2 gets sourced in the jedit.bash rc. I have placed the source command for ROS2. So I was thinking that it is getting sourced, but I had opened the terminal before running the MicroROS agent. So even if it was getting sourced, it was not aware of the MicroROS agent. But this time I started with sourcing the terminal first. Once MicroROS agent opened, first sourced the terminal once again, then it is working. I think most probably the issue is there. If I divide the screen after MicroROS, then this issue won't come. I think that was the main reason, because everything was same. I just sourced it this time. So these are the fine things which we have to look while debugging, and this is how you have to use the command line tools for debugging. Okay, so good that the issue came, so that you got some idea about debugging as well, how to debug. So okay, so till here, okay, I wanted to show you guys this thing, no? Yeah. So in the TF, you have show names. So I'm not able to zoom because my mouse is disconnected due to the port issue. So basically, the fixed frame which you are seeing is the odom frame, and the moving frame which you are seeing is the IMU link. So odom frame is fixed, and in the Madgwick filter we saw that we wanted the fixed frame or the world frame as odom, and we wanted that it should publish the TF between IMU and the odom frame. So this is what we refer to. This is what is happening. Continuous TF is being published between the two, and the IMU link is moving, and the odom is like fixed. If you don't put odom frame, these things cannot be achieved. So I just wanted to show you guys this, tell you guys this. Here in the global options, you can see the fixed frame is odom here. If we try to fix it to IMU link, then let's see what's happening. Okay, so IMU link is fixed. Now odom frame is moving. So since our visual, which is the cylinder, is connected to the IMU link, now, and since we fixed it, so visual is not moving, the cylinder is not moving, but rather the odom frame is moving. So it is a relative motion between the two. Whichever you fix, other moves. Basically, this is what is happening. I wanted to show this only. Okay. So what doubt we have? Forgetting about sourcing is the main issue which we ignore after building the workspace. Yeah, but the thing is, something new happened. I did not forget sourcing because whenever I open a new terminal, sourcing is happening at the backend because I have the jedit.bash rc, there I am sourcing. But here, sourcing happened, but after running a command, again you have to source. So this, like till now, I've been working so long, this issue never came, but in this workshop, this issue came. Glad that it came. All of you guys learned something new along me. Okay. So we have this thing ready. Now I will disconnect it. Now I will just go to the GitHub repository, and here I have included the bot URDF because we are running out of time and won't be possible to show how these things are done, the description files and all those things. I have already covered it in the edge avoiding video, which you can find on YouTube. Everything is built from scratch in that. So what you guys can do, just clone this repository and use the commands given here so that you can also run it. You have to just run this command, ROS2 launch bot bring up. So what I will do now, I will, since I already have this robot, the Gazebo robot differential drive in my PC, I will just run it. So it is present in the bot workspace. For you guys, you'll have to clone the repository and do that. So I'm going in my bot workspace. I am sourcing it, source install setup.bash, and I will do ROS2 launch from the bot bring up package. I want to run the simulation. Okay. So this is the simulation you should see. So this is the simulation of the edge avoiding robot which we built. So in our case, for now, we will have to remove the table. So let's remove the table. So how will we remove the table? Or let's not remove the table. I have already removed the table in a different workspace. So let's leave it. Let's go to the IMU workspace, which I built, which I have uploaded on the GitHub as well. Source install setup.bash ROS2 launch bot bring up. From there, I want to launch the simulated robot.launch.py. Here I have my robot and the table I have removed. So this is the robot. The URDF is ready. The world is ready. The controllers have also been added. Everything is ready. If you just do ROS2 topic list, you will see all the topics here. So for our thing, we only are concerned about this topic, wheel controller command well unstamped. So we will be publishing the command velocity, which we will be getting from the IMU to this topic. And when we publish to this topic, the robot will move. For example, I'll try publishing to this topic from the terminal only. So how will I do that? ROS2 topic pub, and I want to publish to wheel controller command well unstamped topic, and the message type for this topic is geometry messages twist, and it has this type structure, linear and angular. So let's give it an angular velocity of 1 radians per second and a linear velocity of say 2 meters per second. If I press enter, you can see that the bot is moving at the backend. And since it is publishing at a frequency of, I guess, 1 hertz or so, this terminal, so this bot is moving in jerks. If I increase the frequency of publishing, it will not move in jerks. Okay, so here you can see the bot moving. So we are only concerned with publishing to that topic. We will be publishing the data to that topic and the bot will be moving. That's the benefit of using, that's the power of topics in ROS2. Everything is ready. We, instead of publishing it via command line, we will publish it via IMU. So we just, it made the thing so modular. We just remove one block and placed another. The entire structure is same. So this is the benefit that ROS2 offers, the framework. You can just interchange between things. But if there were no topics and the nodes were hardwired, then you cannot just directly remove this node and add another. So that's the benefit of topics. It makes it more scalable and modular. Okay. Let's now. Here we will just write one more controller node. What this controller node will do is, 1 second. So what this controller node will do is we have our ESP32 publishing the IMU data, and we publishing it to this topic IMU. What we have this bot in Gazebo. GZ is for Gazebo. We have this bot in our Gazebo, and it subscribes from command well topic, command well unstamp topic. For example, I'm writing in shortcut. So command well topic. So I just want to make a node. Here I will make a controller node. What the controller node will do, will subscribe from this topic and will convert this IMU data to command velocity or velocity commands and publish to this topic. So I just added this section in the middle, the controller node, which is connecting these two topics. And from this node, velocity commands will be published to this. And once again, our bot will start moving in Gazebo. So basically, this is the idea what we are doing. And let's do that. Let's implement that quickly. Could you just show again how to give the motion to bot using IMU? So the command is this. This is the command. ROS2 topic pub, the topic to which you want. Okay. The topic to which you want to publish, the message type, and the values which you want to publish. So why we are using linear X and angular Z? Again, it has been covered in the previous workshops which are available on YouTube. So, and we are running short of time as well. So this is the command basically I have shown you guys. Okay, so now let's quickly write the controller node. IMU controller.py. Yeah. Go to GitHub. From here, IMU visualizer. I will go to IMU visualizer package, IMU controller. I will copy this, paste it here. Okay, this is a very simple node. Again, interpreter and all these things you guys already know. This is the function which is used to convert quaternion. Since using IMU, we are getting the values in quaternion because the calculations were happening in the firmware itself. But here, since we are using it and we want an intuitive understanding, we are converting back the quaternion to Euler angles, which is RPY, roll pitch yaw. Again, this is a function, but I don't remember the name of a package. There is a package known as TF transformations. It is a Python package. So in that, there is an inbuilt function to convert quaternion to Euler, but I haven't used that. This is the function which you can, like this, it does manually in front of you, but you can use that package as well. Package name is TF transformations. And yeah. Okay. So here we have our main class IMU to twist. So the aim is to convert the IMU values, not exactly to twist values, but the behavior to twist values. Like for example, when I move the IMU forward, I want the linear velocity of the robot to map itself with the IMU. Like I have moved the IMU by 45 degree, I want the robot to move at 1 meters per second forward. I move the IMU at 90 degree, I want the robot to move at 2 meters per second. So this is nothing but mapping. If I rotate the IMU about Z axis, I want the robot to rotate about Z axis. That is, I want to publish the command velocities to angular Z, the angular Z I want to publish velocities to. Okay. So again, here I have defined threshold, which is the minimum threshold, which we will see as we move further. That why have I defined threshold is when I'm holding the sensor is very sensitive. Even if I'm not moving my hand, the sensor will still be publishing values. So I've defined a certain threshold that if the sensor values are within 0.1 radians, then don't move the bot. Only when it exceeds that, then move the bot. So whenever the sensor angle in y-axis exceeds 0.1 radians, move the bot forward. Accordingly, map the values. Basically, threshold is set for that purpose. Similarly, threshold is set for this. Linear speed, maximum speed, I have capped it to 2 meters per second. And angular speed, again, at 1 radians per second. So the catch is here, I have like specifically put this thing. For example, if I start my IMU like this, I am holding my IMU like this. So when the node will start, it will start at this reference position. So this is what this command is doing. So, calibrated false. So IMU is not calibrated. Once the node will start, it will record the current value of this IMU and it will do all the calculations with this current value. When I move my IMU like this, so it will find the relative difference between the current value and the moved value. It will find the difference and do that. So for that reason, calibration is very important. So for example, I had kept my sensor like this in a lying down position. So it will get calibrated like this only. And then with this position, every data will be calculated with this reference. So that's the reason for calibration, so that things remain absolute. Okay, pitch offset we will look at. So here is the main thing. We are creating a publisher and this publisher is publishing twist message type to this topic which we just saw to move the robot, and IMU is subscribing from data filtered. So which is this topic? This is the topic to which the Madgwick filter in the launch file was publishing while I showed you guys the remappings. Here in the remapping, you can see this Madgwick filter is taking the raw data. No, first, this smoother node is taking the raw IMU data, which is coming from ESP32, applying the moving average filter to make it smooth, then publishing to this topic. From this topic, Madgwick filter is taking the IMU data. It is doing more processing on it, and then finally it is publishing to output to this topic, IMU data filtered. And this topic we are finally subscribing from the IMU data, and here is the IMU callback. It is checking if the things are calibrated or not. Once it is calibrated, then the difference is being calculated. Here the quaternion is being calculated, and the main logic of this is here. So basically, again, this is This is the calibration process. So initially the pitch offset was 0, but when I was holding the sensor like this, it had a certain pitch. So that pitch is recorded as the initial pitch, and all the values, next values, will be taken in reference to this. If I move my hand, then this value will be calculated, the pitch value, the difference. That is calibration. Here you can see relative pitch. Relative pitch is current pitch minus, let me show it visually once so that you get a better understanding. So this is what I'm referring to as calibration. For example, when I ran the node, I was holding my sensor like this. So this is the initial value which the sensor will record. Of course, this position will also have certain values, X, Y, Z. So this is the initial value which my sensor will record when I move my sensor to this angle. So it is calculating this difference. This is what I'm referring to as calibration. If I calibrated my sensor with initial angle as this, it was facing like this, and then I moved it like this, then I say, for example, moved it like this, then the difference will not be this, but rather the difference will be this. This is what is calibration, the importance of calibration. It sets the initial value, and with reference to this value, all the values will be recorded with the difference. Okay. So here again, the relative value in the y direction is being calculated for linear velocity. Here the relative angular velocity is calculated. There is a catch in it, which I will show you guys later. For linear, I am using angles, direct radian I am using, but for angular z, that is for turning, I am using radians per second. Due to some reason, I will show you when we move to Gazebo. Okay. So here it is checking that relative pitch, that is the difference between the initial value and the current value. Is it greater than the threshold? That is okay. If it is greater than the threshold, means some real movement has happened. If it is not greater than threshold, that means it is noise, just eliminate it. Once it is greater than the threshold, I am publishing the linear speed based on this value. So what am I doing here? So basically I have given it like move in steps. So for example, I have my linear speed set to 2 meters per second. So the relative pitch, for example, the difference is 1, or say, what is this, 45 degree, and I have moved my sensor by 45 degree. So the output for this will be 1. So 1 into 2 is 2. So like that, when I move it like this, then it will become 4, and so on. Since I have capped it, so it will not be greater than 2, but this is what it is doing. It's just for gradient thing I have provided. You can call it the proportional constant as well, which we use in KP or PID. Okay, so here we have, okay, so if the threshold, the difference is not greater than the threshold, then just stop the robot with velocity 0. Same is happening for angular velocity. Same thing is happening. And then we are finally publishing the twist message. And here is the entry points and all those things. These are fixed. So here the twist message is getting published. So let's see it once, then I'll explain it further. Then you'll get a better understanding. So to run this, again, you'll have to create a launch file. IMU controller.launch.py. In the launch file, so this is the launch file, and since I have written a new node here, so I'll just uncomment it in the setup.py IMU visualizer node. Sorry, IMU controller node, and I will make it an executable in the which workspace? Gesture workspace. I'll go in SRC, I'll go in IMU visualizer ls. There are 2 nodes. I'll make it executable IMU controller. So it has become executable since it is green now. Okay, so we have the controller node, which will subscribe from IMU topic and publish to command velocity topic, which will indeed move the robot we have the controller launch file. Here we are doing nothing. We are running the smoother node, which is like applying the moving average filter with a window size of 15. We are changing it via parameters. Here we are using the Madgwick filter again for further processing. Then we are running the controller node, which we just wrote. This controller node we are running here, which accepts data from IMU, publishes it to the topic, command velocity topic. This is the final launch file. Let's try to build it once and run it. Then we will come to the code once again. So for it to run, let's source everything. Source CD MicroROS. Let's source this as well. Let me connect. Okay, now once it is connected, then I'll source the system once again. Okay, so it got connected. Source everything. SC, once again I sourced. This one also I'll source. Now I will launch Gazebo. So for that I'll go inside IMU workspace. I will source, install setup.bash. I will do ROS2 launch, and my package is bot bring up in that simulated launch.py. Okay, so I have my Gazebo running now. Let's source it once again, and let's go to gesture workspace, which we created now, and let's source install setup.bash. Now in this I want to launch from IMU visualizer package. I want to launch the IMU. Okay, we did not build the workspace, no? Call con build. Let's build the workspace first. Got built. Let's source it once again. Now let's launch ROS2 launch IMU visualizer IMU controller.launch.py. Let me hold this sensor like this so that calibration happens here only. And when I press enter, things should work. Let me see Gazebo. Here you are seeing that Gazebo is Gazebo is let me try to zoom in. Okay, so here you can see when I am holding the sensor still, the bot is still, and the threshold is working fine. So when I move the bot about z-axis, you can see that the bot will start rotating. But when the moment I stop the sensor, the bot is again still. This is happening because, as I told you, for z-axis, I am using radians per second. So it will only detect the movement as long as it is moving. Once the motion stops, then velocity is 0. So it is only detecting change. It is not detecting absolute value. But for linear, I haven't put radians per second, but rather radians. So when I move it forward, you will see that the bot is moving forward continuously, but it is not changing direction because it is moving forward based on the angle. If I had put linear velocity same as angular velocity, then the bot would only move when the sensor orientation changed, then it would stop. But for it to move continuously, let's bring it back. Let's rotate it and bring it to ourselves. So based on the angle, the speed is increasing. For right now, I've kept the speed slow. the maximum speed, so it is slow, but you can increase it using the parameters. Let's turn it this way. Let's move it forward. You can see that the bot is moving based on the sensor values. Right now I've tilted the sensor, it is moving forward. Moment I rotated it, yeah. So this is what is happening. And here you can see all the values. Here you can see radians per second, and here you can see radian. So since right now the value is 1 radian, so the bot is moving at a velocity of 1 meters per second. And the bot, this direction is not changing because it is radians per second. And the threshold is set to 0.1. The moment threshold increases from 0.1, like right now I increased the threshold, so the bot direction changed. Yeah. So this was it. So this was the code. Where did the code? Yeah. So this is the difference between radians per second and radian. So initially I had put radian in my code, but it was only moving as long as the sensor detected a change. Velocity is nothing but change. But for me to move my bot forward, I want it to move forward when I move my hand like this based on my gesture. So there you put radian, but you want to rotate only when there is a change. So till there is a change, it will rotate. The moment it is stopped, change is 0. It will only move forward in that direction. So this was the code, and this was the final project which we successfully completed on time. And now if you guys have any doubt, you can just let me know. Okay guys, so this was it for the session. Hope you guys enjoyed the session. Okay, guys, thanks. Then I'll end the meeting. Bye.